All right. Welcome back, everybody. Let's put our laptops away. Okay, have a seat. How many people saw that amazing game yesterday? Anybody? Giants? Yay? Working on nachos. They won. All right. So, okay, so last time we started talking about devices, and we kind of mentioned that there's at least three categories that people typically think of as devices in modern systems. Those are block devices, character devices, and network devices. To some extent, the fact that there are these categories is a little bit physical. I mean, certainly the difference between block and character devices, you could imagine being physical. Network devices are more of a historical difference, and the interface typically is different enough that it makes sense to keep them in a third category. But as you probably realize, a lot of what happens in operating systems is historical. So, but we're going to keep these three categories as they are. Block devices are things that you access in blocks, surprisingly. So things like disk drives, tape drives, CD-ROM, flash devices, most of the big ones that you might have in cameras are all block devices. And typical system calls are things like open, read, write, seek. Okay? And often with these block devices, you can memory map them as well. So you could take a file and you could map it into memory using mmap. And as a result, you end up with a file that takes up a chunk of memory that you can read and write by reading and writing memory. Okay? Character devices are things that tend to go in bytes. So keyboards, mice, serial ports, USB devices of some types. And these typically are a single character at a time, and the system calls are things like get and put. And usually there are libraries on top that let you do things like read lines or parse data, etc. And then finally, network devices are things like Ethernet and wireless, Bluetooth, okay, all of these that you're used to. And mostly the network devices you're all going to run into are accessed by a socket interface. Okay, and what's a socket? Well, we'll spend more time talking about that in a week or two. But basically, a socket is an endpoint to communication. You need two sockets. You connect them together. You write data in one socket. It comes out the other side. Okay, and if it's a bidirectional stream, you write it in the other side, and it comes out the first side. Okay, so that's a socket. Is basically a generic endpoint for communication. And incidentally, the socket interface was developed here at Berkeley originally. Go Cal. This was in the 4.2 BSD release, and this was such a big deal that this was one of these cases where people were waiting, runners were waiting for the final tapes to be made so they could grab the release and run off to the businesses where they were using it. So this was a big step forward. Okay. Any questions on these three categories? Yeah.
When you say like a block device, does that mean that a whole block of like bytes is transferred before the operating system is kind of interrupted and told that there's data for it?
Yeah, I would say the fundamental characteristic of a block device is that you can't get a single byte at a time. It's always chunks. And that's a hardware limitation. And the one that I might have said earlier that may have surprised a few of you is that those flash keys or things that you put into cameras, many of those are actually block devices because you can't write single bytes to them because they have to be read and written in blocks. Actually, they have to be written in blocks. In some cases, you could read them independent of that. Good. Any other question? Yes?
Wouldn't it be almost assumed that anything with the file system would be a block device because it would be very difficult to build sockets just by that?
You could build a file system with byte addressing. This is just a question. I mean, what's a file system? We haven't talked about it, but it's, one characteristic is there's some naming, so you can look up the name, and then that gives you a stream of bytes, and if you think about the way you typically access files, it's very byte-oriented. You seek to a certain byte You read from that point some random number that doesn't necessarily have anything to do with the size of the block on the disk. So I actually would not limit file systems to block devices. It turns out that the traditional ones tend to be block devices, but that's not a requirement. That's a good question, though. Any other ones? Okay, so then there was a different thing that we went on to, which had to do with the timing of accessing these devices. And we started out with kind of the standard blocking interface, or the wait interface, which is you go to do a read or a write, and what happens is your thread is put to sleep until it completes. So in the case of a read system call, the read goes to sleep, the data comes back, and then you get to continue. Okay, or in the case of a write, you actually go to sleep until the write has finished, and then you come back. Okay, so this almost goes without saying, right? This is the way you probably have thought about read and write, since, I don't know, you started playing with them in kindergarten. So the other options, though, are a little different. There's the non-blocking and the asynchronous interfaces, and these are subtly different. So in the case of non-blocking, you sort of say, well, do whatever you can immediately for me and tell me how much you did. So I say read 100 bytes. It says, well, here's 2. Okay, now, why might it only be able to return 2? Yeah. Could be end of file, but in that case, you're actually, a blocking interface could return only 2 in that case, too, because it'd say, well, I can't get any more. What else? Yeah. User hasn't typed them yet. Yes. Okay. What else? Yeah. Network hasn't received the packets yet. Maybe it's a file system built out of block devices like usual, and you asked for 100, but the first 2 are on the block that was already loaded internal to the operating system, and it has to go to disk to get the next few bytes. It says, well, I got 2. Here, you can have them right away. So that's a non-blocking interface. You can get back, you get back a status of how much was actually accomplished. The case of asynchronous, you get back a promise. Yeah, okay, I'll do it for you when I can. Okay, and so here the difference is you say, give me 100 bytes, and it will give you 100 bytes, but it will return to you immediately, and later you'll get signal and say, here's 100 bytes. Okay, so does that make sense, those two differences? Okay, now this asynchronous version actually requires some sort of callback. So typically you register what I would say is kind of like a user level interrupt handler that says, okay, run this function when the data's back. Okay, whereas this non-blocking is literally, yeah, I do the read system call, it returns immediately with a number of how much it did, but it didn't necessarily try to do everything if it couldn't do it immediately. Okay, we good? Good. All right. So today I want to get some traction on I/O systems, and then we're going to dive into a particular type of I/O system, namely a disk, and we'll even throw in a little queuing theory at the end of the lecture. So we'll see how that goes. So first of all, this is a fairly old chipset, but Intel has been doing this kind of thing for a long time. And basically, notice this little orange piece is the processor, which is almost uninteresting relative to the rest. Okay, so you have the processor, yeah. And then you've got the chipsets. Typically, north and south bridges are often the way they're called informally, but then this is also called the memory controller hub or the I/O controller hub, so MCH and ICH. And notice that what's off of the north bridge is fast things, so we have DRAM and graphics, and then off of the ICH is basically everything else, which typically is slow. So we've got serial ports, we've got USB, we've got audio, we've got BIOS, we've got other things. We've even got buses for disks and so on. Okay? All right. So why do I say that basically this set of things here is slow, whereas this set of things is fast? What's slow versus fast here, do you think? Yeah.
I mean, if you look at the diagram of the bus, the north bridge are
Yeah.
multiple gigabits per second, whereas the south bridge are
Yeah, so these are little, look at this, 150 megabits, 133 megabits. These guys are gigabits per second, gigabytes per second in some cases. So basically, we want to have a very fast path from our DRAM to the processor and from our graphics to the DRAM and to the processor. These need to be really fast. This, the aggregate bandwidth coming out of these other I/O devices is, it's a little bit, so we can have one chip handle it all, and it really doesn't do much, doesn't matter. All right? Any questions? Yeah.
Yes, how could the CPU be slower than the memory? It seems like
Yeah, that's a good question. Why is this only 6.4 gigabytes per second and this is 8.5?
is that the capacity or is that like
No, that's a bandwidth. Yeah.
Well, typically you can only read a byte at a time, like the DDR2 interface only allows you to read a byte at a time, so you actually have to read it faster.
So one thing might say that this processor is going to something that's not aligned according to the memory, so we have to read more than we actually send to the processor. Okay, that's one possibility, yeah. Okay, processor is not always reading and writing to memory. Well, what you notice over here, we actually have the graphics, right? So graphics is accessing memory independent of the processor. Okay, so we also need extra bandwidth there. Okay? Question, yeah.
it's also possible that the memory controller is on the North Bridge, right?
Yep.
Is there extra traffic between the memory controller and the memory that the processor doesn't know?
Well, there's some refresh traffic, but usually that's not that high a bandwidth. Okay.
Well, you also have the I/O and I/O
Yeah. I mean, yeah, exactly. So,
if you look at the sum of them, it's about 8.5.
yeah. So also the other thing that was mentioned is that potentially you've got memory going directly to the devices here too. And we'll talk about direct memory access in a second. That's a good point. Okay. All right. So what's interesting, I guess, is if you're a processor designer like Intel, typically you come out with a new processor and then you immediately come out with what's called a chipset. And the chipset is these guys. Okay, it's a set of chips that goes along with the processor. And oftentimes when they, every version of the processor comes out, often comes out with a new version of the north and south bridges. Okay. So how does the processor actually talk to a device? So if we look here, abstractly, we've got the CPU is getting memory from a processor memory bus. And if you notice, you could kind of say, well, the processor memory bus is some combination of this hub bus and some internal switching to get to the DRAM. Okay, and so that's kind of, when we were talking about caches and all that sort of stuff, there's that little bus. But you can see I've jammed it up top because that's not going to be the primary thing I talk about here. Typically off of that bus is a set of adapters, okay, that are going to talk to other buses and an interrupt controller. Okay, and if you take a given device, like for instance here is, let's say this is a graphics device of some sort. That device is talking through a bus adapter to the memory bus and being able to give interrupts to the interrupt controller. And if we look inside this device, typical devices have a bunch of subpieces to them. So there's an interface to the bus, which is, got to be there in order to speak the right protocol. There might be a bunch of memory inside. So in the case of an actual graphics device, there's typically a lot of memory for where the display images go. There's typically a set of registers that control the device. So by reading and writing these registers, you put it into different modes, like, use VGA mode, or, use really high density graphics mode with automatic rendering. Okay, you can do that with a bunch of control registers. Okay, and any device you look into is going to have some combination of control registers and memory. And so the question is kind of, how does the processor talk to that? Does anybody know? How does the processor actually access a device? Or maybe the right thing is, what does a device driver have to do? Anybody know?
Load or store word to a particular address and maps these interface.
Okay, good. So one thought is we somehow map addresses here onto our physical memory addresses such that the CPU can read and write them. Okay? What else could they do? Message passing is an answer that's plausible in specialized systems, but not usually what's done here in a standard system. I'll buy that as a possibility. All right, so let's take a look here. How does this actually work? Well, there's kind of two ways, I/O instructions and memory mapped I/O, and I wanted to make sure that we had these distinct in everybody's mind. So there are certain processors, not very many, but they're also the most popular ones in the world, like the x86 processors, that have I/O instructions. And what an I/O instruction is it's like a load or store, but rather than talking to a memory address, you actually talk to the special I/O space. Okay, and so if you actually look, there's typically a set of ports that they're called, which are really addresses in the I/O space, and by executing an in or an out instruction, which is like a load or a store in the special I/O space, you end up reading and writing control registers on the device. Okay, so a device driver needs to know kind of where the control registers are mapped so it can execute the right in and out instructions in order to do I/O. Okay? The other option is memory mapped I/O, which was the first thing that came up, which is we'd actually take some of these various parts of the system and we map them into the physical address space. The CPU then can just read and write them by mapping them with its page tables. Okay? Does that make sense to everybody? So by the way, memory mapped I/O is by far the most popular thing because not all processors have I/O instructions. However, if you ever actually tried to write a device driver for x86, you're going to run into I/O instructions because they're there, they've been used. You almost can't avoid them. So let's take a brief look at how this might work. So here is a typical physical address space for some device, and notice what I've got here is I've got registers, so we're going to ignore the I/O devices for a moment. I've got registers here like status and command registers, which are part of the physical address space. And then I've got a bunch of memory, which is another part of the physical address space. And as long as the CPU reads or writes these different parts of the address space, suddenly something happens to the device. Okay? So, for instance, by reading and writing 7F004, what happens is I can send a command or look at the status of a command, 7F000, just by writing or reading from those addresses. Okay? Is everybody with me? So that's interesting. It's a little different. It's an active, load or store. You do a store and poof, all of a sudden something appears on your screen, something complicated. Okay? Now, the other option is by writing to display memory directly, you could be putting bits up. So your actual bits that you write here end up showing up as individual pixels or individual colors on the screen. Okay? Another option, which is quite common, so that would be writing directly to the memory, and this would put bits up on the screen. Another option is you might write a set of commands or descriptions of objects. So for instance, graphics controller cards, you might actually write a set of triangles that represent some cool scene, and then you'd write a command that says go, and what would happen is the hardware inside the display controller would go ahead and render that scene on the screen. Take the triangles, put some textures on them, and do whatever you've written in the command queue, and all of a sudden you've got an interesting display. Okay? All right. Questions? Does everybody understand what memory mapped I/O is? Yeah.
So does the graphics, the device, does it possibly hold the memory, or how does it know that something's been written?
Very good question. How does the device know that something's been written to that memory? Go ahead.
One, you don't actually write memory, so you actually just have a mapping to actually a register, and it knows immediately.
Yeah. So that's a great question. So let's back up for a second and take a look here. So the answer is you never actually write to memory. So what happens is a CPU writes to an address that's been mapped to the hardware, and that address comes off the memory bus, and then rather than going to DRAM, the bus adapters say, oh, this is an address that I should recognize. The write goes directly to the device. It doesn't actually ever go to memory. And so it's like a trigger and data all in one, because the act of writing causes something to go to the device and causes the device to wake up and do something. So that's a good question. Yeah.
If you have something like a graphics card, which say
Uh-huh.
If it's memory, I mean, are they usually memory mapped? And does that just make it so that everything else just loses out on that gig of memory and like no other processes can use it at all?
Okay, so there's two questions. So if a graphics card has a gigabyte of memory, does that mean that it's always mapped somewhere so that you can write it? And not always. So notice that in this particular example, there's actually different types of memory, and maybe not all the types are always writable that way, but oftentimes they are. The second question is, if you've got a gig mapped into the physical address space, yes, it means that there is a gigabyte of physical address space you cannot put DRAM in. And you can start to see why having, say, a 64-bit, well, actually, say 40-bit physical address space might be a good thing because you can have much more space for devices. Yeah, question?
So on x86, are the I/O instructions, do they actually have different semantics than the normal memory instructions, or is it just different?
They do have different well, it's a different address space for sure, and it also doesn't go through a cache. So you know that the out instruction is guaranteed to trigger something. So let me address that point since you brought it up. If you're writing to physical address space to trigger something with a device, you've got to be a little bit careful, because if the cache doesn't know that that's a device, then you could write something, and if it's a write-back cache, it just writes into the cache, and it never goes to the device. Okay, so now we have a situation where a cache, which is supposed to improve performance, is actually destroying semantics, because what we write isn't going to the device. Does anybody know how to fix that? Yes? Yes, if you go back and look at the page table entries that I showed you for Intel, there's actually some uncacheable bits in a page table entry which say, when you write to this or you read from it, never put it in the cache or go into the cache, rather go directly to the bus. So, yes?
Same with why if the device wrote something to the memory, and then so then that way when we try to access it, we won't try to go to the cache first because the cache won't have that data.
So that's a different issue. Let's hold on to that question for a moment for when I talk about DMA, because we do have to be careful about the cache again there. So if I don't answer that question in a few slides, ask me again. Okay? Good. Any other questions? So, another interesting thing I'll point out is once you have memory mapped device access, then there's no reason you couldn't give full control to the user in some process of a device. You just map the physical control ports of that to the user's address space, and suddenly there's a piece of virtual memory that they can read and write to that causes the device to do something. Okay, so under control of the operating system, it can choose to give full control to a particular process for a device. Okay? All right. Now, how do we get data to and from the device? Well, what I've been telling you is a kind of a primitive idea here. I've got a load or a store, it goes to the device. What's a little bad about that is if I have to say load, suppose I want to load a megabyte out of a device. Does that mean I have to have a really tight loop with load, 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 load? Okay? And if you think about it, that sounds a little unfortunate because it means I'm tying up processor time to do something that's so automatic it seems kind of silly not to have the hardware help me with it. Okay, but that's what's called program I/O. So every byte or word is transferred by the processor doing a load or store directly to the device. Okay, and that's the easiest thing to imagine. The pros of this are very simple, hardware. It's only the normal memory mapping. The cons, of course, is you got processor cycles being consumed, and it's proportional to the size of data. So if you've got to, pull in a gigabyte, well, that's much more processor. Okay, the other option is direct memory access. Okay, and what DMA is this notion that I can tell a device that it's okay for it to transfer data directly into memory for me, into DRAM. And I'll tell it where to transfer, I'll tell it how much to transfer, and then the processor gets out of the loop, and the device goes ahead and transfers for me, and all I find out about it, or I find out about it later because of an interrupt. Okay, so this is much less processor heavy than other things you might imagine. You can imagine it makes great sense for a disk drive. Oh, I want to pull in a block off the disk. Go ahead and do it, put it in this part of memory, and interrupt me when you're done. Okay, rather than wait for it to get to that spot on the disk and then load it a byte at a time off and write it to memory, and then I know I'm done, but I've also wasted a bunch of CPU. Okay? And your book gives you an example of one interaction of a DMA controller, and I'll walk you through this. And this is not entirely the way it's done on all processors, but it gives you kind of an idea. So the device driver, which we'll talk about in a moment, basically says, oh, I want you to transfer disk data for me to some buffer at address X. So basically the file system is saying, here's a buffer, go ahead and pull the data off the disk, put it in that buffer. The device driver then goes ahead and programs the disk and typically the DMA controller saying, okay, this is the block I want you to grab, here's the address I want you to put the data at, here's the number of bytes to transfer. Then later, the disk controller initiates the transfer after it's moved the heads to the right place. Okay, and it transfers data one at a time. And notice that here's the disk. It's actually the data is going to come off the disk controller, go across the bus, possibly through the DMA controller, and directly to memory, and no CPU involved. So the disk is going to be sort of doing the transfer automatically, and when we're done, okay, when C equals 0 or the number of bytes, then the DMA controller sends an interrupt and says, okay, your transfer's done, and the data you wanted is now in buffer X, and the CPU never had to do any of the actual transferring. All it did was it set up the transfer and then let it go. All right? Is everybody kind of with me on that? Question, yes? Oh, great question. So, is it already a physical address for the buffer? This is, technically the answer could be physical or virtual, but probably physical. More important, though, is if it's a user buffer you're writing into, you need to do what's called pinning to make sure that it doesn't move out from under the DMA controller, because the DMA controller ultimately has to have a physical address. All right, so if you were to say start with a buffer, here's, you translate from virtual to physical, the DMA controller is doing its thing, and now your little clock algorithm, which you're so happy that you just got working, pages the thing out from under the DMA controller. Now you got a mess. Okay, so the notion of the word pin really is about preventing the virtual machine or virtual memory hard software. Boy, I'm losing it today. Your clock algorithm from paging something out from under the hardware. Okay, question, yes. Well, devices, so what do you mean devices aren't protected?
Or rather, memory's not protected from devices.
Okay, good. Memory's not protected from devices. I would say on first blush that's true. Okay, so if your operating system programs the DMA controller badly or incorrectly, you could write all over parts of memory you didn't want to mess with, and you've got a problem. And this is all sort of part of the fact that the hardware itself is only accessible, in the operating system usually, especially the DMA controller, because you can really screw up a system with a DMA controller. Yes?
Do most systems have a way for the processor to set up, like mask out part of the memory so that the DMA controller can't write to it?
So that's a great question. Do most systems have a way to mask out most of the memory so the DMA controller can't touch it? No. And this has actually been kind of an interesting problem as we're kind of looking at new ways of designing operating systems, because the DMA controller is kind of the last sort of non-properly virtualized thing. So it's not really easy to protect against the DMA controller, because ideally you'd like somebody, maybe even a user-level driver, to program the DMA controller, but you give it too much control and suddenly it screws everything up. So yeah, that's a problem. Question, yes?
I can fashion myself a little device that I can plug into my computer and have it just run rampant.
You could fashion a little device, plug it into your computer, and make it run rampant. Well, yes. Depends on what the device driver is and where it came from. This is why you've got to be really careful when you say, okay, oh, we got to download a device driver for this device. Are you okay with that? Okay. Okay. Now, back to a question that was asked earlier. Here's an interesting thing. See, my buffer X, which is coming from the disk, is getting its data directly from the disk to memory. What happens if buffer X was previously used, so some data from buffer X is actually in the cache? Now we've got a problem where the data in the cache gets out of date relative to the data in memory. Okay? What do we do? Depends on the system. So one answer would be you never use a buffer that could be cached. Another is you have to flush the cache for any buffer you're about to do DMA on. So that means walking through it and making sure it's kicked out of the cache. The third option, which is often used in hardware, x86 hardware, whatever, is the DMA controller actually is aware of the cache. So as it's writing to memory, it's invalidating the cache out from underneath it. So got to be really careful of that cache DMA controller interaction. Okay, good. DMA, by the way, has been around since the beginning of time, literally. I mean, the very first mainframes, typically you couldn't afford to use CPU cycles to do the individual transfers because the CPU was so slow and precious, you wanted to do other stuff with it. So building a DMA controller was a natural part of that. And it was only kind of that middle little period of time. Yeah, I'm not even going to say that. So DMA's been around a long time. Okay, good. Any questions? So let's take a brief look at the kernel structure for I/O. So the nice thing about I/O, which I mentioned last time, is that despite the fact that you have a lot of different devices, different structures, different ways of interfacing them, the kernel tries to hide that from the user. So a typical structure has kind of a kernel I/O subsystem which presents a standard set of interfaces to the kernel and ultimately to the user. And inside that subsystem is where the device driver actually fits. Okay, so every one of the device drivers that you load that's going to talk to a device has to meet a certain interface so that basically you can, use that device no matter what, how it works. Okay, so example, you might have SCSI that talks to a disk drive. You might have PCI that talks to a disk drive. You have floppy talks to a disk drive. You might have a USB device that talks to one of your little plug-in keys. In all of those cases, even though every device is really different, you can use a file browser on them, right? You go to the file browser on your USB key, you click on it, you do copy, you go to your disk, you do paste, and it just works. Okay, that's actually pretty amazing when you really think about it, okay, because those devices are very different. And the reason that works is because there's a standardized interface in the kernel that has been developed for device drivers. All right, and if you're interested in device drivers in much more depth, there's a number of books that are written about this. There's one on Linux device drivers that is by one of the O'Reilly books, the animal books. I forget what animal's on it, but take a look. Okay? Linux is a little bit scrambled as to exactly how clean its I/O interface is, but it's definitely there. All right, questions? Now, okay, we're going to go on to Administrivia. So let's, okay. So, the results. So the midterm had an average of 69.9 and a standard deviation of 12. So that's about where I like to have my averages, right around 70, so that was successful. We had a fairly wide variance. We had a minimum of 27.5 and a max of 90.5. You can see it's a little skewed in this direction a bit, but by and large it's pretty good. Since a standard deviation is worth a grade in this class, I would say if you're 2 standard deviations below the mean, you should probably talk to me. Just come in and chat. And I would say probably a good idea to go through your midterm and figure out where you lost points. Okay? All right. Any questions on distributions? Okay. So group evaluations should be in by now. If you don't put in a group evaluation, if there are those of you who are resisting the evaluation process, I would say don't do that because that will risk you having a complete 0 on the project no matter how good you are. And try to fill them out honestly, because your TAs may query you if there's something they see in there. So try to be honest about how your group interactions are going. And if there are group interactions that are not going well, make sure that you come to talk to either myself or your TA or both so that we can debug your interactions. Okay? This is important. You're halfway through the projects. Yes? So what percent of the grade is the midterm? Well, that's going to depend on something I say at the end here, but as of right now, with one midterm and one final, the midterm is 20%. Okay, and the final is 25. Now, if we go for a second midterm, then it'll be 15, 15, 15.
Wait, the final's 50?
15, 15, 15. The projects are 50. The final is worth 123% of your grade. Okay. Now, just kidding for those of you in cyberspace. So the other thing I wanted to say something here because there are a few not so good interactions in groups, and I just wanted to point this out, that this notion that you're going to get exactly the same grade as all of your group members on the projects is predicated on you participating. Okay, and I just, one of the reasons we have you do the group evaluations, and one of the reasons we have the TAs taking careful notes at your design reviews and listening to how things are going, is because we will adjust the point distributions between members in the group if you have a group member who's not participating. Okay, and in some sense it's a zero-sum game, meaning that they'll get more points and a group member who's not participating will get less in unfortunate circumstances. Okay, so that I wanted to point that out in case there were those of you who thought that they could say not participate or not help debug or something like that and get all the points. Okay? Now, this is also why it's very important for your TAs and ultimately, I suppose, myself, if it needs to go there, to know what's going on in your groups if they're not going well. Let us know. I would much prefer that everybody gets exactly the same point total in their group and that you all get 150% of the points. Well, that probably won't happen. But rather than having to, zero out somebody. So if there's a problem, come talk to me. Sometimes a non-participating group member is not participating because they're having trouble with their group, and so you should talk to me if you feel like you're not able to participate. If you've got a group and you've got a member who's not participating, come talk to me. I mean, it can be informally, but let me know. Because this is supposed to be a good programming experience for everybody, so I want to make sure that happens. Okay. Now, so I just said that. Finally, I have a room for the exam. It would be 11:29. I've gotten many comments over email. Please, 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 please have another exam. Yes.
Is there a possibility of having maybe the final be able to cover the
Yeah, I know that. I think there are definitely faculty that do a good final clobber midterm or good midterm clobber final. That just gets kind of tricky, so I don't usually do that. But if you want to do a second midterm, which I'm getting the impression people do, that would bring things down to 15, 15, 15. So, all right, how many people would like to have another midterm? All right. How many people definitely don't want another midterm? All right. Unfortunately, I think the want to have another midterms break the tie. How many people don't care? All right. So I guess we will have another midterm. Yeah. It'll be It'll be midterm 2 material, so this will be testing you on stuff in the second half of the term, not in the first half. And then the final is kind of everything, potentially. So there, yes?
What if you're not going to be in town that day?
On 11/29?
Yeah, the day after Thanksgiving.
Uh,
Or not the day after.
this is the Monday after Thanksgiving. Well, talk to me, and maybe we can do it the day after Thanksgiving. The day after the Monday after Thanksgiving. That would be Tuesday. All right, well, do you want to vote again? No, I want to re-vote.
Can it be a take-home midterm?
What about absentee voters?
Absentee voters. Speaking of which, everybody's voting tomorrow, right?
Yes.
Okay, I won't tell you how to vote, obviously, because that got a lot of people into trouble, and I'd never do that anyway. But definitely vote. Not even off the record. I don't do that, but it's very important for you to vote. Everybody should vote. Okay. All right. If you have some strong feelings about not taking the midterm, feel free to send me some mail. I'll be happy to read it.
It's a trap.
No, it's not a trap. Maybe I'll change my mind. You never know. Okay. I've never seen quite this even of a split, so it's pretty hard to tell. Do an online poll. All right, well, I suppose we could do an online poll. We'll see. The problem with that is that then that's a vote early, vote often, right? We'll need the security aspects at the end of this course in order to do that. All right. Maybe I'll ask you again on Wednesday. You all know when it would be, and you know what the material is. Take a look at midterm 2. But let's move on to this topic. So I'm good either way. I mean, the problem with giving you another exam is that I got to grade another exam. So
One question, true, false.
yeah, one question, 2 false. So what's a device driver? So a device driver is device-specific code in the kernel, okay, that interacts directly with the device. And as I mentioned, it's got a standard interface to the rest of the kernel up. And down, there's basically no rules. Okay, so pretty much device drivers come in every shape and size you could think of, and they come in a wide spectrum of from working to not working. And so the important part is that from the top, the same kernel I/O subsystem can interact easily with different devices. And by the way, seriously, on midterm 2, if you can't make it on that day or something, send me mail so I understand what's going on. Anyway, so special device configuration, which is unique, typically is done in some completely out-of-band fashion. So for instance, in Unix, there's something called the ioctls. So if you do a man on ioctl, you'll actually see about the most random collection of interface things you could possibly imagine. Okay, because different ioctls work for different devices. And one thing you will find, for instance, if you're interested in turning a blocking interface into a non-blocking interface, you'll do it with the ioctl calls. So you'll first open the device, then you'll do an ioctl on that device to turn it into non-blocking or whatever. Okay? And typically, device drivers are divided into 2 pieces, the top and the bottom half. The top half is the part that interacts with the kernel, and it implements a set of standard interfaces that basically look a lot like your system calls with a little more detail: open, close, read, write, ioctl, strategy. So some of these are not things that you give the user directly, but they're pretty much standard interfaces. And the top half is the part that starts the I/O operations and then typically will put a process to sleep until the results are done. Okay, so the top half is the part that knows about processes. The bottom half runs at interrupt level and typically doesn't know a process from a thread from anything else. All it's doing is taking notification that an operation's actually finished, starting getting the DMA to happen. Well, actually, the DMA is often done by then, but basically responding to the device. And it's up to the bottom half to signal the top half, which then figures out what to do. Okay, so the bottom half is the very simplistic thing. It's running at interrupt level. It's got its own stack and so on. Okay. If you look in your book, it kind of gives you the, oh, question. Yeah, go ahead.
What is the necessity of the actual? Why couldn't you just write whichever escape character or something to the device?
So, what do you mean?
Well, you've got the diagonal.
Uh-huh.
Why wouldn't you just write flow characters using the right function?
So the question might be why bother to have a device driver?
Well, why bother having a specific system call for fixing it? Why not just?
Oh, I see. Because you still need to protect the device from the user, or you've got to copy arguments from user space to kernel space. I mean, there's that kind of protected interface part of what system calls do. And if you give direct access to user code to change things about the device, how do you know they won't change something about the device that violates security or something like that? So the ioctls are still a narrow straw that control what it is you allow the user to do.
And there's multiple ioctls for every different device type. So different devices may have 5 ioctl calls.
So usually different device types have sets of ioctls that are similar. And usually you have to look at the specific device to see which ioctls it can use. But yeah, there's actually something called ioctl.h, which is often available in user sysinclude or user include, which you can see what the different ioctls are that are available. And not all of them work for every device. So the life cycle of an I/O request is kind of like this. And notice that the user program might request some I/O. We get a system call. That's how it does the request. So this might be a read or a write. And then we can ask right away whether the system can satisfy the request without ever talking to the device. Okay, so why might the system be able to handle a request without ever talking to the device? Yeah.
Maybe it's memory map, and you've got the data you need already in memory.
Okay, right. I wouldn't start with the statement, maybe it's memory map. Let's pull that one out of your response. And yeah, maybe it's already got the data. And a good example of that would be with a file system, you have what's called the buffer cache, which is a group of memory that's the data sort of stages off the disk into the buffer cache, and it's possible that it's already in the buffer cache. Okay? So yeah, so maybe I can already satisfy the request because I read 2 bytes from the file, and now I'm reading another 2 bytes, and of course it's a block file system, so the file's already been partially loaded. Okay? In that case, I basically transfer the data and satisfy right away, and I'm good. Also, if I have a non-blocking I/O interface, it's possible that I will never go further than this. Can I satisfy the request? Either yes, or partially, or whatever will immediately return, possibly we sort of stab the I/O system and say, well, they really wanted another 98 bytes. Will you please start getting them for me? Okay, so that would be what would happen in a non-blocking case. But in a blocking case, we might say, can we satisfy the request? No. At which point we actually send the request down to the device driver. And the device driver or the top half of the device, either this part of this kernel I/O subsystem or the top half of the device driver, depending on how things are laid out, will put that process to sleep, and it will start the access going. Okay, so at that point we sort of say, well, process, you can't go right now. We'll put you to sleep, and we'll start moving. And then nothing, right? Then the device does its thing. And later, the device is done. Okay, so the device is basically causes an interrupt. And at that point, the bottom half says, oh, what is this interrupt for? Okay, I'm going to signal the top half about some completion of I/O. And at that point, the top half wakes things up, and we transfer the data back to the user, and we continue up. Okay, so that's kind of the interaction between the top and the bottom halves of the drivers. Okay, questions? Now, clearly, if you write a device driver, you have to adhere to a set of interfaces. This is why it's very important, and I'm sure there are several of you in here that will eventually write device drivers for something. It's a specialized skill that can be very satisfying when it finally works. Make sure you read the interfaces first, otherwise you're really going to screw your system up. Okay? But that's where something like that Writing Linux Device Driver book would be good for you if you were going to do this on Linux. Okay? Now this interaction here is a little bit too low level for us to do it in Nachos, so that's why we don't have a Nachos Write Device Driver part of the project. So you won't have to write an actual device driver in this class. Someday, maybe if we have an advanced OS class, you would be writing device drivers. We might actually do that. Okay, yeah, 163. Now that number's already taken, I think. Okay, questions on this? So how does the operating system know that a device is ready? Well, the I/O device has to do something, and there's two kind of primary possibilities here. Okay, one of them is an interrupt. We've been talking about that. The device is done, either DMA transferring data or it's ready for you to do programmed I/O. It sends it sets the interrupt line. The interrupt line causes the lower half of the device driver to start running, and that is a notification that something's done. The other option is, so this is pros and cons. The other option is polling, and in the case of polling, what we actually have is the top half of the device driver, or possibly the timer interrupt, keeps checking. Are you done yet? Are you done yet? Are you done yet? That's polling. Okay? Now, the nice thing about polling is it's potentially very low overhead, because all you're doing is reading or writing from a device driver, from a device register. Are you done yet? Are you done yet? You're looking for a bit to go from 0 to 1 or something. Interrupts, by contrast, are much higher overhead because you have to save all the registers and do a bunch of stuff before you can actually run the interrupt handler, and then you got to restore all the registers and come back. Okay, so interrupts are potentially higher overhead than polling. What's the downside of polling? It's on my slide, but what does it mean? Yeah, the problem is if you got an unpredictable device, you're wasting all this time. Are you done yet? Are you done yet? Are you done yet? Are you done yet? And so interrupts are great for unpredictable behavior because you're not wasting a lot of polling time, right? The lowest overhead thing, when done enough, is high overhead. There's a deep, profound thing that you guys should come away from today's class, right? All right? So actual devices combine both polling and interrupts, and I've given you this example throughout the term because it's a good one. You got a 10 gigabit Ethernet interface. If you were to interrupt on every packet coming in, that would actually overwhelm most processors that you're likely to use because there's just not enough processing power to handle all the saving and restoring of registers and so on dealing with the interrupts if you took one on every packet if it were coming in at highest rate. So what typically happens is the first packet causes the interrupt, and once you get in the interrupt handler, a bunch of other packets have arrived. The first thing it does is it polls until it empties out the network card, and then it re-enables interrupts and goes back to the non-polling state. And so it's a combination of polling and interrupt. You get an interrupt on the first packet, you poll for the rest of them. Okay? All right. Question? Yes?
When you have you're polling, for instance, and the CPU is trying to get the information about whether or not access is made,
Yep.
reading that information from memory, say you got the access directly, or is it, what is it actually touching?
So when you're polling, you're basically taking, either you're doing an I/O instruction, an in instruction to the right port that's a status register in the device, or you've got a memory mapped status register and you're doing an uncached read from that address in the device.
There's a CPU instruction for reading registers on devices.
Well, no, well, either an I/O instruction, or it's a memory mapped I/O address, like we mentioned earlier. Yeah. So it's not special. It's a regular load or store, or it's a regular I/O in operation. Okay, let's take a break. We'll come back and we're going to switch gears unless there are any other questions on I/O devices here. We're going to talk about disks now. Okay.
Well, what actually happens is it's sort of a level triggered thing, so it turns the interrupt on, and then it's up to the software to turn it off again. So it just keeps returning the same bit on.
And this thing seems like most people were always on. And it's 186. Not HLS. He's like the. So, it has been suggested that I should attempt an online survey. How many people think I should do an online survey? All right, I'll see if that's possible in short order. How many people who want the midterm couldn't make it on that Monday?
How many people who don't want them? How many people can't make it on that Monday? A couple of you. All right. All right. Nobody's going to be happy in the grand scheme, are they? All right. Well, I tell you, the reason it's so close to Thanksgiving is that's our last week. It's the last week of classes. So you can complain to the chancellor who cut out a week. It's kind of messed things up a bit. All right. Let's switch topics now for a moment. So let's talk about disk drives. So disk drives to date are the sort of the densest storage devices we've got. There have been several times in the past where memory has gotten close to being as dense as disks, but eventually some breakthrough in disk technology won out. And so from a sort of bit per cubic meter or something, basically disks are certainly it. Well, maybe tapes are better, but nobody uses tapes. Yeah. So you mean you're talking about CD-ROMs or something? Well, DVR is just using a disk drive. Yeah. Yeah, TiVo is typically using a disk drive. You know, the optical devices have a pretty high bit density as well. But so let's just talk about disk drives. The thing that you might not know that's interesting about them is, one, the head is actually sort of fabricated by some of the same complex technology they make integrated circuits with, okay? Because they're very multiple layers of magnetic material and so on. So it's actually quite a specialized industry to build the disk heads, and companies that make disks often buy their heads from other companies. The other thing to note is a disk drive has multiple platters on it in some cases, and we'll talk about that. But as you're all aware, a disk spins. Okay, it's a round thing, right? So inside your disk drive is a spinning device. And what's kind of cool is there are these chips that have kind of been obsoleted by flash now, but Hitachi and IBM made these micro devices that fit into cameras. Okay, and they're actually a spinning disk drive inside, which is kind of cool. It's a 1-inch form factor. There was IBM was one of the first ones to come out with one that actually held a gigabyte, which is a big deal at the time. And unfortunately now, you know, you can get flash that's 32 gigabytes without a big deal. And so they kind of got passed by. But from a technology standpoint, they were pretty cool. So what are some of the properties of a disk? Well, so first of all, since we have sort of spinning platters, you can talk about everything within a ring as a track, and then the tracks are divided up into sectors, and this is where we get our block-based device. Okay, and now the sectors themselves can either be a fixed sort of number of bits, or they could be actually this kind of a pie-shaped sort of thing where you sort of cut a piece of pie out, and the sectors on the outside are longer than the ones on the inside. And we'll talk about the difference there in a second. The individual platters are called platters. Okay. So the head moves in and out, okay, in tandem. So typically, if you got multiple platters and multiple heads, they all move together. It's not like you can have individual heads and different platters move in different ways, okay? Does anybody know why that is? So if you look here, see how these heads are tied? This is tied together with a single stepper motor. So all, N of the heads move together. Why is that? Yeah, it's purely an expense thing, okay? From a low commodity disk standpoint, it makes a lot less sense to have a bunch of heads moving because it's really expensive. Oh, by the way, also both sides of the platter are have data on them, so the heads are double-sided. Okay. So the sector is the independently addressable element, and oftentimes the operating system will take the sector, which is the smallest thing a disk can read or write, and put a bunch of them together and call it a block. So when we talk about a block, that may be more than one sector off the disk. Okay, so if we say that, gee, this paging system has 4K blocks, it could be that the blocks on the disk are 1K or 512 bytes. Okay? And then finally, there's a piece of terminology here. Oops. Oh, well, so much for that. Which is all of the sectors on a given track through all the platters is actually called a cylinder. So you could say the cylinder is the set of all things you can get by not moving the head and just letting the disc rotate. Question, yes? Yes, all the cylinders are different sizes. Now, the question you might ask is, are all the cylinders different number of bytes? Okay, that's a different question. And let's hold that question for 2 more bullets. So some typical numbers, you know, there might be 500 on a low-end disk to more than 20,000 tracks per surface. Okay, and when you're talking about a 3.5-inch disk, that's a lot of tracks. There might be 32 to 100 to 800 sectors per track. Okay, and this question about how many bits are available on a track is an interesting one. If you imagine the simplest thing you could do is, let me ask you this question. When I spin the disk, am I varying the speed of the disk or am I leaving it constant? I'm either shutting it down or it's pretty much a constant speed. Why is that? Yeah, basically there's a lot of angular momentum going on here, so we want to just get it going and leave it going, okay? What's interesting about that is if I were to have the head sitting on the disk and I'm moving back and forth, and I were to have the bits go onto the disk on at a constant rate or come off the disk at a constant rate, what is the size of a sector, say 512 bits, on the outside versus the inside? So if I have a constant rate of bits going onto the disk, what does the physical size of the sectors look like on the outside versus the inside? Yeah. Yeah, they get larger. Why? Because the disk is moving at, you know, it's constant speed, and as I go out to the edge, the disk is going by the heads faster than when I'm on the inside. Does everybody see that? And therefore, if I'm putting the bits out at constant rate, that means that my sectors are bigger on the outside than on the inside, which exactly corresponds to this pie-shaped thing. So, right, the sector that's a little guy on the inside corresponds to a big guy on the outside. Yes? Well, the heads are all kind of, they're going within a cylinder. Every platter in the cylinder has things going by the heads at the same rate, because the heads are just kind of moving in and out. Yes, they move definitely together. So what about the density of bits in what I've just described to you? So if the data is coming into the disk or off the disk at a constant rate and I move the heads in and out, what about the density of bits per unit area on the inside versus the outside? Anybody? Bueller? Yes. Higher on the inside and lower on the outside. Why? Because for constant bit rate, you got a lower speed going around in the inside than in the outside, right? So the bits are denser on the inside. That's the way they used to make disks in the old days. The problem with that is that your density varies. And if you're really trying to cram as many bits on as possible, it means you're wasting possibilities on the outside, because you've got to be able to somehow distinguish some density on the inside. So that's why they have, today is what they've got is called zoned bit recording, where the density is constant and therefore you have more sectors on the outside than on the inside. Okay? Question, yes?
So does that mean that it would be better to have different reads and writes happen around the same, happen in those 5 tracks rather than jumping to like...
Well, so it's always better to not jump much, because it takes a long time to move the head. We'll talk about that in a second. But that isn't, but the bit rate wouldn't be an argument for that as much as just from a latency standpoint, you're not moving the head much. Notice, by the way, that the bit rate now coming off the disk is varying. On the outside, it's much faster than on the inside. Okay? So that means that they never could do this zoned bit recording until they had enough sophistication in digital signal processing to handle the high speed of the bits coming off the disk on the outside and the low speed on the inside, and being able to go smoothly between the two. Yes? So whether the information on different platters is related to each other is totally up to the operating system. So when we talk about file systems, we can answer that question. We don't need to answer it quite yet. So that's a question about how you use the disk, not about what the physical device requires.
You might be talking about the addresses too. So be great to see the address.
Maybe. Oh, okay, that's a different question. That's a good one too. So because of the requirements for high-performance digital signal processing to even pull the data off the disk, it turns out only one of the heads can be active at once. So you can only be getting actually data off of one side of one platter at a time. But if you're reading a bunch of stuff all in a cylinder, it means you can alternate heads without ever moving the actual heads around, and can get high performance off that way too. Okay, another question in the back? No. Okay, good. Now, the other thing you may or may not know is these heads actually float above a cushion of air. Okay, very, very thin cushion. Okay, there's a little bit of kind of an oil depending on how these work, and then basically these are kind of floating on top of it. Does anybody know what the term head crash means? Other than some sort of band or something? Yes? Yeah, so a head crash actually happens, the head, which is flying with atoms worth of air, basically crashes and hits the disk and scrapes your bits off, okay? And they end up flying into the bit bucket and never to be re-got, okay? You can't get them back in that case. All right. Good. Question, yes?
Does that happen naturally? Hard drives just degrade until they have a head crash or they die from other things?
Yeah, certainly if they're jarred, it's a really big problem, right? Does anybody remember the rather amusing, there was a rather amusing ad for, I think it was IBM laptops, where somebody's bragging about how their laptop can handle being dropped off the table because it automatically parks the disk heads on the fly when it detects high impact. And then the guy drops the laptop, his neighbor drops the laptop and says, well, but that wasn't my laptop. But anyway. But yeah, so the best way to deal with avoiding head crashes if you've got high acceleration is to make sure to park the heads on a part of the disk where there aren't any bits. But yeah, they will degrade over time and cause sometimes that will cause a head crash. Okay. So actually, disk drives have to be one of those technologies that are almost magical, because the bits are hundreds of gigabits per square inch, and somehow, with the right combination of disk heads and DSP technology, you're able to actually extract data off of the disk and do it most of the time. So it's actually pretty amazing. I'm in awe of disk manufacturers. But so let's suppose that we're kind of interested in saying, what is the performance of these devices? And so we could ask ourselves, first of all, what are the metrics we care about? So some of the things might be like response time or throughput. So we could say, well, from the point at which I make a request until I get my data back, what is that response time? Okay, and that could involve moving the head, waiting for things to rotate, and then reading the data off the disk, and then I've got my data, right? So there may be multiple things involved in getting my data back. Throughput is a different thing, right? It's how many bits per unit time can I get off the disk? So somebody tell me, what's the way to get the highest throughput of data off of a disk? Yes? Okay, well, let me take what you said and just say never move the heads. Okay, and what else? Yeah? Yeah, you want to read the whole cylinder. And which cylinder? Outside, right? Because the outside cylinder has the highest bandwidth coming off of it. Okay, so when we talk about file systems next time, we're going to be very interested in making sure to optimize head movement so that we never move the heads. Okay, and other things that can contribute to latency include things like the software path. Okay, what from the point which a process makes a request through the operating system, you know, what is that path? How complicated is it? Is it stuck in a queue? And then, of course, the hardware controller has to actually cause the disk to do something, and then the disk itself has to be read. So there's a lot of latency factors here. And I want to talk a little bit about the software one, and we're going to continue this next time. But one of the interesting aspects of any system like this is its queuing behavior, and that is roughly because from the point at which you make a request, it's got to wait inside the system for a while before it gets to the disk drive. That's a queue. And remember, I think I showed you this curve several times this term, where if you have the ultimate, the total utilization of 100% for the disk or any device, as you get closer to 100%, the response time typically grows non-linearly. Okay? And so what this says is, as I'm making that disk more and more busy, my response time is not growing linearly with how busy I am, but non-linearly, and it can actually start to look like it's climbing toward infinity as I get closer to 100%. This is very standard queuing behavior. Okay? Almost any system that you come up with, except for one that's 100% deterministic, will behave this way. If there's any randomness in the system, you will get this queuing behavior. Okay? And so what's the bottom line to this? Never run anything at 100%, ever, if you can avoid it. Okay? Because 100% represents potentially really, really, really slow system behavior. And what I'm going to do, starting this time and finishing next time, and actually maybe we'll even do it next time so we don't run out of too much time, is I'm going to tell you about some very simple queuing models that will illustrate this behavior. And you'll see that there is a 1 over 1 minus utilization term that basically means this thing grows to an infinity with the simple models. But you can see exactly where that comes from. Okay? So our performance model for our disk is basically got to accept the fact that reading and writing data from the disk is a 3-stage process. This is the physical disk. First, we got to seek. And the seek time is bringing the head into the right cylinder. Then there's a rotational latency. Just because we're on the right cylinder doesn't mean we don't have to wait for the disk to go around until we hit the sector we want, right? Because the sector could be on the wrong side of the disk when we first get our heads there. And then finally, there's actually transfer time. And this has to do with whatever the bandwidth is at that cylinder coming off the disk. Okay, so these three physical components talk about the actual disk time. And when we build a model, we actually put in the other two components. So here are the three I just talked about: seek time, rotational time, and transfer time. And then on top of that, we typically talk about queuing time, which has to do with waiting to actually launch the request, and controller time, which is that physical controller that we started the lecture with, right? Remember that little box I showed you that was memory mapped I/O or whatever? There is a controller there that talks to the disk, and there's some amount of time involved in getting that to do its thing and actually start the disk access. Okay, so these 5 terms are a very reasonable model for how the disk is going to perform, which, with the one question, I mean, how the heck can I model the queuing time when it's some really complicated function of the way the software is written? Okay, so you could see that maybe these 4 are somehow deterministic, but this queuing time seems like, almost wishful thinking that we could go after it. And in reality, it is wishful thinking to have a detailed queuing model, but what we'll do is we'll come up with an aggregate queuing model that does reasonably well and can give us some estimates of how this is going to perform. Okay? Everybody with me where we're going? So, and obviously the highest bandwidth in a system like this is transferring large groups of blocks sequentially from one track. Okay. So I think we're going to end there. So in conclusion, we'll actually show you the queuing model next time. So I/O controllers are the hardware that actually control the device. The processor accesses through I/O instructions or load store to memory mapped addresses. We talked about notification mechanisms. We talked about interrupts and polling. We talked about this disk performance and the model of disks. So we have this 5 terms: queuing time, controller time, seek, rotational transfer. And we'll talk next time, for instance, about how the rotational latency is on average a half a rotation and so on. And then finally, we're going to come up with a queuing model, and it'll be very simple. It's a 2-term C and U basically give you a lot of information about how this behaves, if you can just figure out what C and U are. Okay. So should I re-vote next time or what? Just do it? All right. We'll see you guys. Sounds like a Nike commercial.